Hey guys, we're back. This time we're going to do Riemann sum, but instead of using rectangles, we're actually going to use trapezoids. So trapezoidal approximation, not Riemann. Remember that Riemann is rectangles. So for most functions, using the trapezoids to approximate the areas is more accurate than using rectangles. Pretty much it's like your average of your right and left Riemann sum. So the area of a single trapezoid, of course, to remember, is 1/2 the height times base 1 plus base 2. So both of those sides. But what we're going to do, remember that when we do area under the curve, we're actually going to turn our trapezoid over. So we're thinking of it as technically the height would be the width, and your base 1, base 2 would be your height 1, height 2, okay? So I want you guys to think of it as 1/2 the width, h1 plus h2. Okay, and we're going to try to see little other things that we could do for your equation, just like we did with the Riemann sum with equal widths. But if we look at our first example here, we have 5 trapezoids to find this area, and actually this is the same thing we were doing on 6.7, but we're doing it with triangles. And as you can see, guys, our widths are the same, okay? So I'm going to do this full out, and we'll see, because the widths are the same, if we can condense this in any way. So we have approximately from 0, or integral from 0 to 10 of f of x dx is approximately, sorry guys, we have our first trapezoid would be 1/2. The width is 2. Sorry, guys. And then our height 1, which in this case would be 0, plus our height 2, which is 4. And that's our first trapezoid. So now let's go to the second trapezoid. We have 1/2. The width is actually, oh, so these widths are not the same. I just thought because they were doing 2, 4, 6, 8 that they were. So we're not going to do the same widths. As you can see, what's going on here, we go from 2 to 5. So 2 to 5 is the width of what? It's the width of 3. Height 1 is on this left side, which is 4, plus a height 2 on the right side there, it goes to 3. So that's our second trapezoid. Third trapezoid, 1/2 times, let's see, it looks like we're going from 5 to 6, so our width is 1. The height on the left side is 3. And the height on the right side is 2. So that's our third one. Our fourth one, 1/2. Our width is 2. So our height here is 2 and 2. And our last trapezoid, 1/2. We're going from 8 to 10, so that's a width of 2. Height of 2, height of 5. And we're done. So one of the things I do want you guys to notice is that look at these heights in between. We're doubling them, right? See, 2, 2, 2, 2. And then our outer 2 only come once. So that's where our trick comes into play. Now, if you forget the formula of a trapezoid, you can always do the area of a rectangle and your area of your triangle. But guys, really, you should memorize the area of a trapezoid. So example 2 here, we have a table, so we can check on that table, right? So as you can see, if we're doing 4 equal subdivisions, you can see that each of these heights, if we break this down into 4, there's our 4 rectangles. They have the height of 10, and you have your bases. Now, again, I'm going to show you 2 different ways that you can do this. So we have the approximation. Let's do the first trapezoid, which is going to be here, the height. So 1/2, the height is 10, and base 1 is 1.8 plus base 2, which is 2. Then we add 1/2, the next trapezoid there. We have the width of 10, height 1 is 2, height 1 is 2, height 2 is 2.5. So that's trapezoid 2 plus the third trapezoid, 1/2, the width is 10, height is 2.5 plus height 2, which is 3.5, plus the last trapezoid is 1/2, width is 10, 3.5 plus 2.2. Okay, here's a trick that we can do. When you have equal widths, as you can see, we're all repeating 1/2 and 10, right? Because that's our width. Now, if you look, the first height we only use that once, but every height after that, excluding the last one, we use it twice. 2.5 plus 2 times 3.5, but that last height there, we would only use once, just like that first height. So that's a condensed way of writing it. That's up to you, what you want to do. Okay, as the number of subdivisions increases, the accuracy of the Riemann sum approximation improves. So increasing improves it to be more accurate. Okay, to achieve perfect accuracy, we need to approach infinitely many subdivisions. If you remember from secondary 3 and you talk about infinitely many, we're summarizing, we're doing that summation, okay? And it's almost like we're doing that limit, right? Getting very, very close. So how do we set that up? If we have an integral from a to b of f of x dx, we can actually do or set it up as the summation of infinitely many by doing the limit as x as n, so the subdivisions, approaches infinity. We have k equals 1, n is our final because we're trying to approach infinity, okay? And then what we do is we have our lower limit plus k times our change. Well, our change is our width. It's our b minus a over n, okay? So what we're going to do, and this is mostly right here, is with right-handed. When we talk about left-handed, we're going from 1 to n minus 1. Okay, so we're going to write our integral as an infinite right Riemann sum. So the first thing we need to find what b minus a over n is. Well, b is 4, a is 1, so that means we get 3 over n. Okay, so this is our change in x. Then we also have to include inner summation here, or right here. We have to include what a is. Well, a is our lower limit, which is 1. And we have to talk about our f of x, which is x to the 5th. Okay, these 3 parts will help me write my summation. So my summation, we have limit as as n approaches infinity, the summation, right? So we have k starting at 1, all the way going to infinity, right? So n. Now we write in our function, okay? So f of x, but we don't need to say f of, because we know f of x is x to the 5th. So what we're going to say is a, which in this case our lower limit is 1, plus what we would do is k times our b minus a over n. Our b over a minus n is 3 over n. So we have 3 over n times k. Now this is of our function, right? And our function is x to the 5th. So all of this to the 5th times our width, which is b minus a over n. And we know according to ours is 3 over n. So we just wrote our integral as an limit of infinite sum. Okay, what about us going backwards? What if we take the limit of an infinite sum here? How do we write the integral? So we're going to be working backwards here. We know that b minus a over n equals pi over n. Okay, I also know that a, because a is what's added on in the beginning, right? A equals pi over 2. And it looks like that our f of x is just sine of x. Okay, so right now, if we talked about the integral, we know that we have the integral starting at pi over 2 of sine x dx. But what are we missing right now, guys? We are missing the upper limit. How can we find that? We can find it right from here. So I know that b minus a is pi. So I'm going to write b minus, now what was a? A was pi over 2 equals pi. Well, add pi over 2 to both sides, and we end up with 3 pi over 2 as our upper limit. Now, of course, there could be other answers with a shift. What happens is if you do have a shift within your function, that changes your boundaries. But this is the most simplistic way that you can do this, okay? And yes, for the left sum, we would write it as k to 1 to n minus 1. So this would be k equals 1, and n minus 1 would be in the summation right there. And it looks like you are ready to do some practice.